Okay, so here the function is the square root of x. The derivative of the function is 1/2 x to the minus 1/2. So if I want to evaluate the square root of 4.1, I take the value of the function at 4 plus the derivative at 4 times 4.1 minus 4. So the value of the function at 4, I plug 4 into the function, I get 2. Value of the derivative at 4, I plug 4 into the derivative, and I get 0.25. Then I multiply that by 0.1, add that together, and I get an approximation. Square root of 4.1 in a calculator is really close to what I got for an approximation of 4.1. So today, we're going to finish this section, and then I will give you a quiz. So I think we'll have enough time to finish this section, and then I will answer any questions you have on the written homework or on Wiley, and then give you the last 15 minutes for the quiz. And I think that's plenty of time for the quiz. Okay, so local linear approximation. We did a few different examples with square root functions. But let's look at an example of a trig function. Let's approximate sine of a angle. So go ahead and write this out. The main application of local linear approximation is in modeling problems where it is useful to replace complicated functions by simpler ones. So let's look at sine of x. And let's say we're taking points around 0. Because I know sine of 0 is 0. So that's an easy one to plug in. Sine of pi over 2, pi, 3 pi over 4, 2 pi. Those are basic ones that I can approximate around. So the derivative of sine is cosine of x. Very important thing to remember here. This is a radian measure. Doesn't look like it. So when I go and find this out, I can only plug in a radian degree, or a radian measurement. So if I have degrees, before I plug it in, I have to convert that to radians, because it has to deal with the derivative, right? Anytime we're differentiating, we have to make sure that we plug in radian measurement. So if I want to calculate what is sine of 2 degrees, I'm plugging in 2 degrees, but when I plug that in, after I do the local linear approximation to plug that in, I need to make sure I plug in a radian measurement. So sine of 2 degrees, it turns out, is going to be, let me just do the general one for sine of x. That's going to be around this x naught equals 0. That's going to be sine of 0 plus cosine of 0 times x minus 0, right? If I'm doing it about this x naught point. So it turns out sine of x, sine of 0 is 0, cosine of 0 is 1, times x. So it turns out sine of x is approximately x for any measurement around 0, right? So if I want to find sine of 2 degrees, that's going to be approximately x, but note again, x has to be a radian measurement. So how do I convert 2 degrees to radians? Yeah, multiply by pi, divide by 180, and this is approximately 0.0349066 radians. So sine of 2 degrees would be 2 degrees converted to radians. Sine of 3 degrees would be the same thing. Question?
If, like on a test,
Mm-hmm.
do you want that many sig figs?
No. A couple would be fine. I would tell you if it mattered.
2 or 3.
Yeah. So here, if I look at scientific calculator, if I take sine of 2 degrees, so if I put it in degrees, so I can plug in sine of 2, so I believe I take it like this, you can see that it equals this answer, which is 2 in radians. Question?
I don't understand what you did on the sine 0, cosine 0.
So here I use local linear approximation. The function is approximately the value of the function at the point plus the derivative of the function at the point times x minus the point. And I said, okay, I want to look at this point around 0.
Okay.
Make sense?
Yeah, I just forgot that. Thank you.
It's okay, you had a day to sleep, so. Okay, so now if I want to approximate sine of 3 degrees, that is approximately the representation of 3 degrees in radians, right? Because this is my input, but I need to make sure that it's input in radians. So I'd have 3 times pi over 180, which to my calculator, what is 3 times pi divided by 180? So I get 0.052359 radians, but sine of 3 degrees is also going to be just this number. So we can test that. And if I take sine of 3 degrees, because I have it in degrees, so my calculator is going to calculate it, but I hit sine hyperbolic. I just want to hit sine. Sorry about that. No, it's a D. So I hit the right one. So you can see that this number is very close to this number. And it turns out the error is pretty good here. Eventually, if I want to say maybe 45 degrees, or when I get close to 30, when I get close to 30 degrees, I want to change my x naught point to not be 0, but to be 30. Because I can evaluate sine of 30 and cosine of 30. So my equation here is going to change a little bit. The key thing to remember is when you're plugging in your x, because you get a linear equation here, right? Some function of x. You can't plug in the degrees, you have to plug in the radians. And I think in our homework we might do an example of like what is approximately sine of 32 degrees.
So if we have to do it in radians, what was the purpose of showing us in degrees? Because they're so close?
Because we can think about what degrees is. If I say, okay, what's the sine? So pi over 4 is 45 degrees, right?
Oh, you're saying...
And if 4 over, what is 46 degrees?
Okay.
Well, I would have to take 46 times 180 divided by pi to get that into radians. Sorry, I flipped it. Pi. I would have to take 46 times pi over 180. So I could ask, what is 46 pi over 180? What is sine of that? Well, I don't know what that is, but I can approximate it by saying this is really close to 45 degrees, right? Pi over 4. So this is really close to 45 degrees, which is pi over 4, and I know how to evaluate that. So instead of plugging in 45 degrees anywhere there's an x, I have to make sure I plug in pi over 4.
Okay.
Make sense?
Yep.
So yeah, really here the only thing. Okay, so let's do a local linear approximation for around x naught to be 30 degrees. So we might want to find what sine of 31 degrees is, because I can visualize what 31 degrees is, but I need to make sure when I plug it in to my local linear approximation, which may or may not be different, what I'm going to get. So sine of 31 degrees is approximately sine of 30 plus cosine of 30 times 31 minus 30. So you guys see where that comes from? So sine of 31 degrees is approximately, what's sine of 30? So this is 1, 2 square root of 3. So sine of 30 is a half. What's cosine of 30? Times 1. Oh, sorry. Yeah, times 1. So now, this is approximately, it doesn't have an x value, because I already plugged that in, right? If I left it as x, this would be x minus 30, and then I could plug in different numbers. But here, this is going to be 1 plus the square root of 3 over 2. What is 1 plus the square root of 3 over 2? So if I go to my calculator, square root of 3, no, how do I put this in? I think I put square root of 3. Seems reasonable. Plus 1 divided by 2. So 1.1299. That's a 1. 1.1299. So if I plug in what would be sine of 31, oh, I hit divided by 2. So 31 degrees sine of that. I think I hit the wrong order on the square root. What is the square root of 3 plus 1? What is it? 2.73. So if I hit 2 square root of 3, and then you hit 3 square root of 2. I don't know the y and the x, the order here. The square root of 3.
And then add 1.
Was this the correct?
Yeah.
Okay, that's the correct one. And then if I divide that by 2, I get 31 minus 30 is 1. So I get this number. Is that at all close to sine of 31?
Is the square root button up in the top right corner?
This, yeah, okay, so square root of 3 plus 1
Divided by 2.
divided by 2, which is a different number than what we got before. Compare that, and it's still off. So sine of 30 plus cosine of 30. Cosine of 30 is square root of 2. This would be. Oh, this is our problem, and this is okay. So this is an angle measurement in degrees, right? So this is degrees. So I need to convert this 1 degrees to pi or to radians. What is 1 degrees in radians? What is it?
Pi over 180.
Very good. Because this is 1 degrees, this 1 degree difference, but I have to make sure I put it in radians.
So, you're going, so I don't have to switch modes in my calculator between degrees and radians because I'm
Definitely
starting with
not.
sine of 30 degrees?
No, so here's the thing is, when I plug it in the calculator, I am calculating what is sine of 31 degrees. This is a linear approximation, and I cannot plug degrees in a linear approximation because I've differentiated sine.
Okay.
So I've differentiated sine, so I can't plug in this is a 1 degree difference, but I need to make sure that it's a radian difference.
But why are we allowed to use sine of 30 degrees at the beginning of that?
Because I'm plugging into a calculator where it knows it's in degree mode.
Oh, and that's how you're getting the
Yeah.
1/2.
Yeah. So if I said find the local linear approximation of sine of 31 degrees without using a calculator. This is what you would do.
Oh, and you know what? I'm sorry. You totally have the triangle drawn over there behind the calculator too. Right?
Yeah, I do, to
Okay,
find out what...
I was going to say, I know this 1/2 of the square root of 3.
Yeah, so here's a triangle for 30 degrees. Right?
Yeah.
Okay, so does that make sense?
Yeah.
So something that I try to be really careful on, I kind of slipped on that. So it's very easy to do. There's a 1 degree difference here, but I can't measure it in degrees. I have to measure this side on radians. So now let's calculate it. So I have the square root of 3 plus, or sorry, this calculator is a little weird how I have to input things. So the square root of 3, square root of 3 times pi, so times pi, plus 1 divided by 2. And I don't know if I did the right series of buttons.
Forgot the 180.
Oh, I did, divided by 180. So I have this divided by 180. Okay, let me do this different. So square root of 3. You guys can do this in your calculator, probably a lot easier than I can in this calculator.
Square root of 3 plus 1.
Okay, here we go. So we can see what this looks like. So yeah, I take 1 plus square root of 3 over 2 times pi over 180, and I get 0.02 question.
Would you have to multiply square root of 3 over 2 times pi over 180 and then add 1/2?
So this is multiplied by this, so yeah, you would. Order of operations. Yeah, so I would have 1/2 plus the square root of 3 divided by 2 times pi over, where's pi at? Fourth down the left side.
So I think you're right.
I don't see it. Here. Pi divided by 180. So I don't even know if I have, oh, divided by. Can I get this back? Divided by 180. There we go. So now if we compare that to what sine is of 31, and that's better, right? Now we're happy. Okay, so thank you. So now if I wanted to say, okay, well, what is sine, since I've already done this work, what is sine of 32 degrees? Well, that's 1/2 plus square root of 3 over 2 times 2 pi over 180, right? Because this would be 2 degrees in radians. And I'm 2 degrees off from 30, right? And I could plug that in my calculator and verify it's a close approximation. Very important on doing a problem like this that once you get in terms of, if I do it in terms of x, sine of 31 degrees is approximately sine of 30 degrees plus cosine of 30 degrees, let's put x instead of 31, is x minus 30. So sine of x is approximately 1/2 plus the square root of 3 over 2 times x minus 30. So this is in degrees, so I need to make sure after I put this in degrees, how many degrees am I off from 30? I need to convert that to radians to do my calculation.
So you could do, in that thing, you could do the quantity or whatever the result is of x minus 30 times pi over 180.
Yes.
And then all of that has to be in parentheses before you multiply it.
Yeah, so this would be in radians. Because we think in degrees, but we need to calculate in radians. So I'm 1 degree different here, but I'm really pi over 80 radians different. Because, question?
What does your calculator need to be in radians?
Here, your calculator doesn't need to be in anything because you're not taking sine or cosine of anything. This is a linear equation. I'm just plugging in numbers. right? If I'm 5 degrees from 30, say I'm at 35, then I take 5 times pi over 180 times square root of 3 over 2 plus a half. There's no calculating. But if I want to evaluate what is sine of 35 degrees, I need to make sure it's in degrees. Or convert 35 to radians and plug it in radians.
I'm still getting different answers.
Then what's your calculator say sine of 32 degrees? Does it say 0.52?
32.
Yeah.
Yeah, it's like 13. But when I do like the calculations, like just regularly.
So probably order of operations is what's getting you. So here you need to, this is being multiplied by this, and then you're adding 1/2. Question?
Which triangles do we need to know? 30, 60, 90?
45, 45, 90, yeah. And then, I mean, if I do something like something that's like a 45-degree angle in the second quadrant, you would know it's 90 plus 45. So you would just know, okay, that's a 45-degree angle in the second quadrant. But your calculator can also calculate what is sine of 30, what is sine of 180. So you don't have to necessarily, yeah. But I need to see, this is really what work I want to see. I want to see what is the local linear approximation. So I might say approximate a number around 30 degrees and leave it as x. So you just need to know to multiply this by pi over 180. But know how to get this. Well, that's sine of 30 plus the derivative of sine at 30, which is cosine at 30, times the difference in x minus 30 degrees. But then after you do that, you need to convert it into radians.
Could we leave that top part and then just on the side have the pi?
Yeah,
100? Okay.
you could. Okay, so that's local linear approximation. And the second part of this is differentials. So I have about 10 minutes to go over this, or 5 minutes, but it doesn't take that long. So you get into a little bit of debate of who actually invented calculus again. Newton, Leibniz, there's also Lagrange. All these people were working on the same concepts at the same time. They use this different notation. And it turns out a differential is just dy and dx separately. So if you think of my function y equals x squared, I can find the rate of change of y with respect to x is 2x. But I can solve for dy equals 2x times dx, right? So I can treat dy as a differential, the change in y. So the change in y is related to the change in x and our x point. So if you think of the graph of this function, if I'm at x equals 1, so at x equals 1, then the change in y is going to be 2 times the change in x. So if I move x over to 2, if I move x over to x equals 2, then dy is going to change 4 times that amount, 2 times 2, right?
Didn't it only move 1 though?
X moved 1, but y moved 4, right? Because y went from 1 to 4, right? X goes from 1, then y is 1. At x equals 2, then y is 4. So the change in y from 1 change in x, it had a change in 4 of y.
So we use the new, I guess the thing that's confusing me is if it's the change in x, the 2 minus 1.
So you're thinking of the actual function. I'm thinking of the relationship of x and y. So here, x is changing. X can change, but y can also change along with this function. When I differentiate it, I get the rate of change of y with respect to x. So this would be a relationship of 2x. So I can solve for dy, and this is very similar to delta y when your rate of change is very, very small. Now, my rate of change is large. It's not a good approximation, just the whole local linear approximation. So your book goes into define the difference here, and it says that recall that the derivative of x is really the limit as delta x goes to 0 of the change in y over the change in x. It's a very simplistic way to write the derivative, right? Because we're taking basically when my delta x goes to 0, my 2 points are the same. And that gives me the slope of the tangent line. So if the change in x is close to 0, then you can let dx equal delta x. So that's saying delta y is approximately the derivative of the function times dx, which equals delta y, right? If I differentiate a function and I solve for dy by itself, I always get the derivative times dx. So last second, Wiley. So looking at the assignment for 3.5, pretty straightforward local linear approximation. Again, local linear approximation. I think you can go about doing that one. This is approximating two other ones. And this is here where the differentials come in. So find the differential. Now you're not finding dy dx, you're just finding dy. So what would be the derivative of 7x cubed minus 4x squared?
X times dx.
Very good. All of this, oops. So all of this is times dx, because I have dy over dx is the derivative, right? And if I want to solve for dy by itself, I multiply it by dx. So then this would be 21
Can you
x
just write that in where
squared.
you have to use a button for dx?
You can, I believe you can write that in. Is there a button for dx?
I know.
I don't see one. So yeah, you would just write dx. But you need parentheses. And the same thing here, you use the product rule and then take it times dx. Very similar idea. You're solving for dy by itself. Here, you're going to use this local linear approximation to approximate the change in y when x is changed from 2 to 2.04. So your dx here is 0.04. So you have an equation for dy. dy is approximately delta y. So you're just plugging in 0.024 for delta x. There's a change in x here. Does that make sense? So I'll give you guys, you guys can look at this. If you guys have any questions, we'll talk about them next time.